For line of best fit and correlation. So this is actually taking the scatter plots to a whole new level. You guys have made scatter plots before, where you just plot the points and kind of see where they are and maybe answer a question or two. But we're going to take it one step further and do line of best fits, which implies right here that you're going to do predictions. Right? So that's really what this is about, is prediction. And this type of mathematics is used by anybody in the financial sector, economists and people work in the stock market that use to predict, like, will the stock market go up next week, down next week, and what should we buy or sell in order to make a profit? So there's ways to take data from the present or past and then figure out, well, based upon this information, what should we do in the future? And your ability to do that really depends on something called the correlation, which is not the correlation. So what's the relationship between all the different points? There's a little summary right here about it is strong or weak. And it's basically, if you're to draw a straight line, in your guys' case, a straight line through all your data, does it come close to all the points or not? Okay? That's what these numbers mean. So you can see like a 1, -1, all the points are really close. Technically a 1 means all the points are actually on the line. So what you're seeing right here is closer to like a 0.8 or something like that. Not really a 1, but they're kind of rounding up. But a 0.5, think of it as a percentage, like, there's 50% of the points are pretty close. And something like a 0 would be like 0% of the points are close to a straight line. So right here, you can't draw a straight line and get close to all the points. So there's no correlation whatsoever. That means there's no relationship between where the points are and where you can put in that straight line. Now you notice when we draw these straight lines, they're pretty close to every point. So it's not like up here going exactly through these, because then they'd be too far from all these points. Right? So when you draw the line, it needs to be close to all of them. It might go like in the middle of them, it might go one direction or another, but it needs to be close to all of them. Give you a different perspective, and this is something we're going to do next week. Well, actually, no, we're going to do this tomorrow. Now, that here's an example of an r equal to 1. So that's the number you're looking at. That's the correlation coefficient. So when we say r, that's just a number. And I'm going to press this, and these points are going to move away from the line. And you can see this number go down. So, of course, the highest it can go would be 1, because that's 100%. Can't go higher than 100%. But as it changes, you can see the lines move away. Right? Now it's only at like a 50%. So this would be a good example of a 0.5, 0.499, but that's pretty close to 0.5. And if you keep it going, you see it gets closer and closer to 0. This is almost 0. So they're nowhere close to a straight line in any sense. No matter how you draw a straight line, it's not going to be close to it. So use this as your guide to help you estimate your correlation. There's also this r squared, which you're not going to worry about. If you take statistics, you'll use that number a lot too. You guys are just going to be looking at this value right here. Tomorrow I'll show you how to go through and do this on Desmos. So today is really do it by hand and learn the basics, and then tomorrow you can do it on Desmos. If you guys take statistics as opposed to pre-calculus, after Algebra 2, you'll be using a calculator or computer or something as opposed to doing everything by hand usually. Okay, so for now, let's just look at these, and you're going to draw a line of best fit, okay, which means draw a straight line that's close to all the points. So this, number one, useful to use a straight edge. And then pick like a y-intercept, and then try to move it a little bit and try to find, well, where is it close to all of them? So something like this might be pretty good. It's These are about equal distance from here to here than they are from here to here. This one's a little bit further away, so I had to make my line a little bit close to this. Now, everybody's line will be different. Now, this is strikingly different from what we just finished with most algebraic maths, where, like on the quadratic stuff, we did the same problem 4 different ways and got the exact same answer. So there's really one answer, and you can get all these different ways. All of us, once we draw our own line, will have a different line and have a different answer, and they're all correct. As long as they're all the same vicinity, they're all correct. And later on, you guys are going to find the equation of this line, which will all be different slopes or different y-intercepts, which will all be correct as long as we're all pretty close to each other. So it's strikingly different from what we've been doing, where you must have the same answer all 4 ways. You might do 2 different lines for the same exact data, have 2 different equations, and they both count. They're both valid estimates. So you got to change your thinking a little bit as we go into statistics. And it doesn't have to match somebody else. It will be close, but it doesn't have to match. So based upon how close I drew my line to all the points, what would you say the correlation is here? Not 100%, because that means the points are exactly on the line. But yeah, 0.7, 0.6, something like that. I mean, up here it's saying use like 0.5 or 1, but it's probably somewhere in between. And just remember this, you need to, like, here is, right, that's 0.6 right there. So that's pretty close. Here's 0.5. There's 0.5. So they don't have to be too far off the line for it to be only 50%. So remember, 100% is exactly on the line. All right, so yeah, this could be like a 0.55 or a 0.6, something like that, I'd say. And it's just an estimation. And this, because it's a positive slope, will be a positive correlation. So think of this as the sign here. The sign has to do with the slope direction. That's the sign prop. The number has nothing to do with slope, by the way. So don't think that 0.5 is like, okay, it's like 1/2 of 1 over 2. It has nothing to do with slope. Just the sign alone. So over here on example 2, naturally the sign would be, you drew a line of best fit here, the sign would be negative, because the slope is negative. And it's not going to be 100%, so it's going to be like negative, I'd say, I don't know, 0.6, 0.60. Could be a little bit higher, 0.7. Not too bad, right? Describing the closeness of all the points to the straight line, and then also the direction of the line itself. Okay, what about here? Is there a straight line you can draw that's close to all of them? No. Yeah, if you drew a line like this, all the points are really far away. If you drew a line like this, all the points are really, there's no straight line you can draw that's really close to all of them. So this would be a good example of a zero correlation or no correlation. Come on there. No correlation. Not close to anything really. Sorry. Alright, so let's do one that's completely from scratch. Go ahead and let's graph this and draw the line and see what the correlation is. I'm going to start off by numbering these correctly. So we have, what's the biggest number we need to graph here for the y-axis? Goes up to 8. So do we have enough room to count every other square?
All right, so if you have the room, remember you want to use it. You don't want to just put everything on half the graph. So we can count every other square, and the only way you'd know that is if you count out the squares and find out, oh, there's 16 of them, so I can use every other square to count as one. Always trying to use as much of the graph as possible. On the other hand, the x-axis goes up to 9, and there's still only 16 squares. We need 18 to go up to count by 2, so here we can only count by 1. I'm going to label every other square just so it doesn't get too crowded. But this way I'm using the maximum amount of the graph possible with what I have. Okay? Now, we can't really graph 4.037522, so it helps to go through just to figure out what you're really going to graph. So yeah, so really it's going to be 2, 4, 3, 7.2, and then we can't do 4.18, but we can do 4.2. It can't do really 4.76 and all that, but we can round it up a little bit and do 4.8. .04 can just be 1.0. 2.43 would just be 2.4. So it helps to go through and actually find what's going to be a little bit more helpful here. Okay. So we got 1,8, and just plot all these. 1,8's up here. We have 2,4. 3,7.2. And 4,4.2. And 5,4.8. And 6,1. And 7,1, 8,2.4, about there, and 9,1.8. All right. And draw a line of best fit that gets close as possible to all the points. One straight line that gets close to all the points. So maybe, yeah, something like this. It doesn't have to go through a point necessarily, but if there's one that's kind of in the middle of all of them, you can use that. And estimate plot of the points that says determine the R and the correlation. So the R would be roughly what? Would be positive or negative? Negative. And this could be like what, 0.5, maybe even 0.4. All right. Maybe less, maybe more. It's just an estimation. Now, it says two things. Find R and the correlation. The R is this right here, of course. The correlation is this, a description of the relationship. So in our case, you could say like it's weak, a negative weak or weak negative correlation. Okay. All right, so that's part one. It's just finding the correlation. All right, so moving on. Here is the real reason for line of best fit. It allows you to do the predictions. So once you get this line of best fit, and you can find information or a prediction for something that you haven't really collected. So like here, these yellow diamonds here are different data points that we actually collected, and by drawing a line of best fit through there, we can now estimate, well, what happens at 21 degrees? Right? What are the ice cream sales going to be? And it's going to be about 480. So you can kind of see how business-wise this could be useful. You can kind of predict, well, next month is supposed to be really hot or it's supposed to be this hot. We can predict how much money we expect to get that month. That way we can figure out like how much we can save or how much we can spend now because we plan on making this much money later on. So it's essential to do this, to run a business, to do this type of mathematically, not just like, oh yeah, this summer I think it's going to be pretty warm. I think I'll make $1 million, and just start making up numbers based on hope or I think, but actually using data and information to make decisions. That's how a company will last years and years and years and decades, as opposed to somebody else that just kind of makes things up and just says, oh, I think it's this, without real evidence on how things really are. Because we can sometimes think one thing, but that's not necessarily reality. So you want to have actual data to back up what your decisions are for making more, for making less, or whatever else. So we want to go through a process here where we can draw our line, find the equation, and we can use that to predict. Okay. Now we're going to use it to actually predict here, which you can actually use the graph, but later on you're going to actually use it to predict in the future. So like stock markets and things like that, if you get enough data and you know how to graph it, you know how to do everything, super precise, it can be more accurate. So you can actually, use it to buy, sell stocks and mutual funds and all this other stuff. Have some sort of financial sense of, and tell people what they should do with their money so you can make them money. And again, if you can do that really well, that's something that pays a lot of money. You can make money for other people. It could be very useful to somebody. All right, so let's go through and label the graph, which is already labeled. Let's go ahead and plot the points. So we have the points plotted. Let's draw the line of best fit. All right, so let's go ahead and draw a line of best fit through here. Now, as you do this, your line might be a little bit different from mine. It's okay. It won't be too different, though, because the points are really close to each other. Use a straight line. Yeah, I think I'll go with that right there. That's pretty close to all the points. Yours might be slightly different. That's okay. So step one, find the line of best fit. We did that. And step two, student has predicted predict if a student has 10 absences. So here's the absences. Go to 10 and estimate from here. So going straight up. Wrong way. straight down. So it'd be right about there. That's 10. So we want to look to this side and say, well, 10 is about how many? A nice straight line, and to me that looks like, I don't know, like 60, maybe 8, 67. So again, straight lines are important here. You can't just draw, some messy line by hand and then do the same thing here. You need some sort of straight edge for guidance. All right, so let's say 68. Okay. So 68%. So that's about a D plus. Okay, so if you're absent, according to this, if you're absent 10 days during the semester, you expect to have maybe like a 68%. Remember, 90 to 95% would be like an A, 80 to 89 would be a B, C, 60 to 69 would be D, and then the rest would be an F. So it kind of makes sense that the more you're not at school, the less well you do on the class, right? Have to be here to learn the material. Now, pick 2 points. Now, I happen to have some that are pretty close here, and I need to do the same thing and estimate. Well, roughly what are these coordinates, since they're not given to me? So I could say that's about, I don't know, 11.8. And estimate this direction, be like 60. And do the same thing here. That's about 5.8 at about 80, 84 or something like that. So we got 5.8 and 84. Okay. Now, if it was like the last one where they actually gave us the chart, we might be able to use these, but you can tell like here, there's only one dotted line, so I would just pick one and figure it out. It doesn't have to be on this list. It's just any 2 points on the line, and any 2 points you pick should give you the same slope. Right. So a little information about slope. Remember that the y's go on top when you're finding slope, rise over run. And of course the bottoms will go, or the x's would be the bottoms. So we have 84 and 60, and 5.8 and 11.8. And we get about, let's see, 24 over -6. Is that right? 7, 6. Okay. So roughly has a slope of -4. Now, 99% of the time that will not come out even. That just happened to be, it just happened that way on this one. So don't expect it always to come out a nice number. You might need a calculator to do this division right here on most of them to get them to be accurate. Okay. Next, estimate the y-intercept. Now, we have a little problem here, is that our graph doesn't quite go high, so I'm just going to have to estimate as well as I can. Like this would be 100. So I can say that'd be like 105 as a y-intercept. Right, that's 105. So y-intercept b equals 105. So the total equation, y equals negative 4x and plus 105. So what I want to do now is go back and remember how we estimated with the graph what grade 10 abscesses would be. I want to plug in 10 into the formula and kind of see if I get a similar answer. So we get 105, right? So it comes out to be negative 40 plus 105, which would be roughly 65%. So from the graph, I end up with 68%. From my equation, I got 65%. Both of them are valid. Both of them are correct. Just because they don't match doesn't mean one's wrong or one's right or they're both wrong. It's just we use two different methods, one from the graph, one from the equation. And since the equation was 100% estimation and the line was 100% estimation, they're going to be different answers. But they should be close. If you got one that's 68%, the other one came out to 32, obviously there's something wrong with one or the other. But as long as they're close, and they're close to other people's as well, then you'll probably be in good shape. And so there is almost a whole problem from beginning to end. You guys didn't have to graph it. So the last step is to, well, get the original data, graph it, all the data points, then do the line, then do the slope, the y-intercept, the estimating, all from scratch. So when we get down to number 2, that's what you guys are going to do. Take this information and do everything from scratch. So these take a little bit of time, but that's what happens when you get to higher math. You have fewer problems, but they take a little bit longer. Okay, so don't think it's, as far as difficulty, it's not harder or easier. There's more steps involved. All right. So step 1, you have to graph the data right. If you don't graph it right, everything else will be wrong after that. So it might seem like the simple step, but there are mistakes made often, so be careful. So for instance, since you see like here, the data starts at 7, it doesn't mean you start at 7 on the axis. This is still 0, 0. You can't just start at 7 because that's your first number. So we're still going to count 1, 3, 5, 7, 9, 11, 13, and then 15, and that'll get everything up to 14, the highest number. Let's see here. For the next one, we got to count from 26. We got to go up to 40, basically. Yeah, that's the highest one. So I'm scanning, trying to find the maximum point for each axis. So I know how much I have to count, and then I can work backwards. Well, 40 needs to be the absolute highest. And you usually don't want it at the very top. It can be, but try not to. In this case, I think it comes out that way, that if you count every other square, it's going to be 5, 10, 15, 20, 25, 30, and 35, 40. So if you can use the whole graph, do it. Don't just use half the graph and count up to 40 and you're at the middle here. You can use the whole thing. That's what you want to do. The more graph you use, the better. And don't forget to label your axes. Small but important detail. So this is going to be number of boats. And this will be years since 2000. Now, why do they use year since 2000 as opposed to year? because if you try labeling this, this would be, 2001, okay, 2003, okay, this is 2005, this is 2007. You can see how crowded and messy it gets when you just use the actual year. So this is a little technique they use just for presentation purposes only. Now, if you're using a computer software or something like that, it'd probably line it up all nice and be very legible. So it just depends on how you're creating your graph, whether it's by hand or by computer. All right, I'll let you guys work on the rest. Use the number 1 right here as a good model on how to go through and find everything.
Wait, the 40 comes from the point you chose, right?
Yep. So these just come from those are the 2 I chose. You notice how 1340 was actually on the graph, but I had to find another one where it went through evenly. So I chose like 312. Technically, it might be 312.5, but I just rounded to 12. Remember, it's an estimation. It's not going to be exact. It's not going to be perfect. That's why our answers are all going to be different, but they'll still be close. But I didn't want to use one of these other blue points from the data because they're not on the line. So one of them was, one of them's not. And depending on which ones you pick and how you drew your line, these numbers will be different. So again, I don't expect you to get 2.8, but it should be close. 2.5 to 2.9 should be somewhere close to that, depending on how you drew your line. And then since we want to find 2020, it's as if the question is, let's predict the future. If we continue this going out 17, 19, and finally 20, and we continued our line of best fit, what number of boats would I get? But we're not going to do that without actually doing the graph. So this is where the predicting comes into play without a graph. We don't have any data for the future, obviously, because it's the future. So we're just going to have to plug 20 in for our x and calculate it. So 2.8, for me, it's going to be 2.8 times 20 plus 5. So 2.8 times 2, 5.6, and then with a 0 be 56, and plus 5, so mine comes out to 61 boats. Okay. That'd be the number of boats in the year 2020 expect to be in the marina, based on my line of best fit.